Hello, hi, good evening, everyone. Today we will start off with a concept known as moment of inertia. Now, understanding moment of inertia is actually very easy. If you will go on to the derivation, definition. So the definition will actually say that moment of inertia is simply the product of mass and square of their respective distance. What does that mean? That imagine you have this particular axis as your axis of rotation. Yep. So we have learned about axis of rotation a lot in the last class. Now imagine there is a point mass m over here. Of course, it will have a perpendicular distance from the axis of rotation. So what are the things over here? First of all, the mass is m and the distance between them is r. So if you simply want to calculate the moment of inertia of this particular mass m, point mass m, the formula is mr square. Very simple. Similarly, if there are more than one of that, imagine like this is the axis of rotation and there is point mass 1, 2, 3, and so on, a lot of them. So I will say m1 r1 square, m2 r2 square, m3 r3 square, mn rn square, and so on and on, where r1, r2, r3 is basically the distance from the axis. That's it. Now this is the definition version of the explanation of moment of inertia. But if you will ask me, how will I define? Very easy. It will be very easy. Just like we are replacing displacement by angular displacement, velocity by angular velocity, acceleration by angular acceleration, then force by torque, momentum by angular momentum, work, power, and time are scalar quantities. That's why they are not changing. Exactly in the same way, we can say that mass will be converted by moment of inertia. What does that actually mean? Now imagine it is it in this manner. We all know about the formula force is equals to mass times acceleration. Now the rotational version of force is torque. Rotational version of mass is what? Moment of inertia. And rotational version of acceleration is what? Angular acceleration. So this is kind of a new formula for torque in relationship with what? Moment of inertia. Yep. Similarly, if I want to define the angular momentum, so first of all, momentum is equals to mass times velocity. Now momentum will be simply converted into angular momentum as L. Then mass will be simply converted into I, and velocity will be converted into what? Angular velocity. So angular momentum is also equals to I into omega. Yep. So exactly in the same way, when we actually say that uh, that momentum is actually a conserved quantity, we can also say that angular momentum is also a conserved quantity. Now, similarly, we can actually make another formula as well. Now, just imagine what is the formula for kinetic energy. Kinetic energy is equals to half mv square. And now if I want to make a formula for kinetic energy in rotational form, so it will be what? Half into moment of inertia will be mass will be converted into moment of inertia and velocity into omega. So this is also a formula for kinetic energy, but in rotational form. Okay. So this is how you can actually make most of the formulas in this chapter. Already this chapter is tough. So you should deal with this chapter in a proper manner. Yeah. Now, have a look onto a very simple problem over here that there is a triangle. On that triangle, there are three masses, M1, M2, and M3. But the axis of rotation goes from between like this. If I want to calculate moment of inertia, so what should I do? I should do, of course, M1 R1 square, M2 R2 square, M3 R3 square. But I need to know about the R1, R2, and R3. And now you will see that mass M1 is 0 distance away from the axis of rotation. That's why it's a 0. Similarly, mass M2 is a by 2 distance away from the axis of rotation. That's why like we are using a by 2 over here. And similarly, the mass M3 is also a by 2 distance away from the axis of rotation. And that's why we are writing this. Similarly, we can do it for all the other things as well. Fine. Hello, Afra, am I audible? Now, there are actually two theorems which we use a lot while we are understanding the concept of moment of inertia. Okay. Now, to understand it, first of all, let's make a formula for a circular ring. Usually, there are a lot of derivations, but we will not be doing all of them. It's not necessary. But we have to understand what is the methodology we actually use to calculate the moment of inertia. Now, the formula which we have actually made right now, that is I is equals to mr square, is a formula for a point mass. But when I'm talking about a ring, let's say if I'm talking about a disk, if I'm talking about a cylinder, these are not point masses. What should I do then? So what will I do? I will take a ring and I will take a certain section of the ring. Okay, very small section of that ring. I will calculate the moment of inertia of that small section. It's kind of a point mass right now. Once I'm done with it, then I will integrate it for the whole ring. Yep, that's the whole point of integration, that you can calculate a small portion, then you can integrate it for a whole range. Similarly, let's say if I'm talking about a rod, so for a rod, you can calculate a very small section and then you can integrate it for a very long rod as well. Yeah, this is how we will do to calculate the moment of inertia of any body. Okay. Now, how to do it? First of all, let's take a ring with a radius r over here and a small section on it that is equals to dx. Now, the length of the ring is of course 2 pi r. That is the circumference of the ring as well. If you want to calculate mass per unit volume, it will be like this: mass by total length. Now, if you want to calculate the mass of this section only, so what we will do, we will actually like multiply mass per unit length by dx. We can do it very simple. Why? The reason is, just like we do that, oh, if I multiply by density into volume, I get mass. Over here as well, it is behaving like a length density, linear density. Okay, so this is behaving like a linear density. If I multiply it with dx, I will get the mass of this section. Now, once I'm done with it, after that, it's very easy. Why? Because calculating the moment of inertia of a very small section, we know that it is equals to mass into r square. Yep, that's the formula. Now, of course, just integrate it from a range of 0 to 2 pi r. Why 0 to 2 pi r? Because you are starting from here. Let's say it is 0. You will take a whole turn. You will come back, and how much distance you have covered? 2 pi r. So just do that, and you will simply get the answer as mr square. That's it. That's it. But now the two theorems I was talking about. The first theorem is theorem of perpendicular axis. What is it useful for? So this is useful. Imagine there is a point P whose moment of inertia I know. with respect to the x-axis, with respect to y-axis, because they are y distance and x distance away from the respective axis. Okay. If we already know this data, then I can easily calculate the moment of inertia along z-axis. Ignore the derivation, not required for now, but you can say that if I want to calculate the moment of inertia along z-axis, which is r distance away, and r is under root y square plus x square, very obvious, because if you will see this particular triangle, so this is kind of a hypotenuse, this is like a perpendicular, this is base, so it makes sense. Now, if this is true, then we can say that moment of inertia along z-axis is simply equals to moment of inertia along x and y-axis separately. Done. So first, when we are done with this, then we can actually use it in a different way. How? So what happens? Let's say we have already calculated for a ring which is actually what? Perpendicular from the surface. What does that actually mean? Have a look like this. Imagine this is a ring. So if this is a ring, and if I'm talking about an axis which is perpendicular like this, yep. So if it is perpendicular like this, we have already calculated moment of inertia is mr square. You might think that, sir, this is not different at all. This is the same formula we learned for the moment of inertia as well. Okay, it is not different, but now it's going to change. How? Yeah. Have a look on to the two diameters over here. Imagine there are two diameters, diameter number 1, diameter number 2. You can take any of the two diameters, but why are we taking two perpendicular diameters? Because now they will act like three perpendicular axes. That is, imagine x-axis, this is the x-axis, this is the y-axis, and this is the z-axis, just like that. Now, what can we do according to theorem of perpendicular axis? Moment of inertia along AB, which is a diameter, CD, which is a diameter, if you will add them, you will get a total moment of inertia along this particular axis, which is YY. Very easy, very simple. Now, because they both are diameters, moment of inertia along them will be equal, which is ID plus ID. And finally, you will see that moment of inertia along the diameter is half mr square. Very simple. So now it's a different formula, but this different formula came from a formula which we already knew. So I will recommend you something that only remember this one, and all the others you can easily calculate if you know the theorems. What are the theorems? The first one was the theorem of perpendicular axis. Second theorem is what do we call as theorem of parallel axis. Again, you can ignore the derivation for now, but my point is, what is theorem of parallel axis? Imagine there is a point mass m, which is x distance away from the axis which is passing through the center of mass. Again, I am repeating, this is a whole body which is having a center of mass here. So there is an axis passing perpendicularly over here. Now there is a point mass m. If I want to calculate the moment of inertia of this body, so it's very simple. But now I am given a random axis PQ. This is a random axis. There is no center of mass. There is no relevance of this axis right now. But the thing is, this axis is parallel to the axis passing through the center of mass, and it is at a distance of d. So if you want to calculate the moment of inertia along a random axis, which is parallel to the axis passing through the center of mass, you can use the formula moment of inertia is equals to moment of inertia along the center of mass plus md square. That's it. That's it. This will be more than enough. Okay, this will be more than enough to calculate the answer. Imagine like this. Now, what we have already done till now, we have calculated the moment of inertia of the body from the perpendicular axis like this, passing through the center. Yep. Then we have also calculated it along the diameter like this, diameter like this. These two things we have done. Now, imagine if they are saying, let's say the next situation. Yep. The next situation is like this. About a tangent in its plane. What does the tangent in its plane actually means? So this is a ring and there is a tangent like this. So it is like this. Yep. Which means the ring will rotate along it like this. Yep. If you want to calculate the moment of inertia along this tangent, do you need to do a whole derivation separately? No, not at all. Why? Have a look. You already know the moment of inertia along the diameter, which is half mr square, and now it is also passing through the center of mass. So what can I say? Moment of inertia along this tangent will be equals to moment of inertia along diameter, because it is also passing through the center of mass, plus mr square. Why mr square? The formula included md square, where d was the separation between the two axes. Exactly in the same way, r is the separation between the two axes. That's it. That's it. Yep. So this is how you can calculate the moment of inertia along any other axis using the parallel axis theorem. Yep. Similarly, what if the situation is like axis perpendicular to its plane? So this is the axis, and this is also an axis which is tangent but perpendicular to the plane as well. What does that mean? So this is a ring. This is passing from the center of mass, which we actually calculated from the start, mr square. But now I have an axis like tangent like this. So if I have an axis tangent to tangent like this, how can I calculate it? Again, I will use the parallel axis theorem and my work will be done. That is, moment of inertia along this tangent is simply equals to moment of inertia along this axis passing through the center, plus mr square, means the r is the distance between the two axes. That's it. So it will be mr square plus mr square, which is equals to 2mr square. That's it. Done. We are completely done. So this is how you can actually calculate the moment of inertia for any other thing as well. If I'm talking about circular disk, so you all know what is a disk, what does a disk looks like. So for a disk, the moment of inertia passing through the center, it is half mr square. But for the diameter and for the tangent, you can calculate using the perpendicular and the parallel axis theorem. Okay. Similarly, if I want to talk about a solid cylinder and a hollow cylinder, the axis passing through their center is half mr square and mr square. Now, of course, there is a whole derivation for the cylinder as well. There is a whole derivation for the disk as well. For now, I will recommend you not to go for the derivation. You can practice or read them, but right now it's the time for doing much more questions as compared to derivations. Okay. So I will tell you the methodology again. For a disk, you will take a very small section like this. Yep. A very small section with a thickness dx. You will calculate the moment of inertia for that, and then you will integrate it for the whole disk. Similarly, you will do it for a cylinder. Then we will do it for a hollow sphere as well. So for a hollow sphere, 2 by 3 mr square. For the tangent, 5 by 3 mr square. Yep. Then we go on to a solid sphere. A solid sphere passing through the center, 2 by 5 mr square, passing through the tangent, 7 by 5 mr square. That's it. Last thing is what? The moment of inertia for a uniform long rod. So it is like this, that for the passing through the center, the moment of inertia is equals to 1 by 12 ml square. Yeah, where length is actually, what do we call? Length is this. That's it. And for axis passing through the end, 1 by 3 ml square. That's it. So last thing is moment of inertia for a uniform lamina. For a lamina having a length L, breadth B. What is a lamina, by the way? You can imagine a cardboard or something like that. Moment of inertia will depend on length as well, breadth as well. That's it. Very simple question on this. Like, for example, in this question, mass is given, length is given, breadth is given, as well as thickness is given. If you want to calculate moment of inertia, you can use the formula, but thickness has no use right now. So you can do it. My point is not this type of easy questions, no. So there is a question like this, for which we have to understand the concept of radius of gyration. Now, whatever you actually do, if you talk about disk, cylinder, ring, or whatever, you have calculated the moment of inertia, but you can also calculate one more thing, that is radius of gyration. What does that mean? Imagine again, there is an axis. There are certain point masses which are R1, R2, R3, R4 distances away from the axis of rotation. So moment of inertia will be simply M1 R1 square, M2 R2 square, and so on and on. Yep. But if you will put the moment of inertia equal to mk square, okay, so you will find something like this. That is, the k is actually equals to RMS value. What is RMS right now? RMS means root mean square. You are doing the root, then you are doing the mean. Like if there are 10 distances, you are dividing by 10. Of course, it's like average. And last thing is square, R1 square, R2 square, R3 square, and so on. And very simple, very easy. This was radius of gyration. I will give you one example. Let's understand it with the example of, let's say, cylinder. So if I want to talk about a solid cylinder, so the moment of inertia for a solid cylinder is half mr square. But if you will put it equals to mk square, where k is the radius of gyration, so what will happen? M and m will get cancelled out, and k square will be r square by 2. But finally, you will get that the k is equals to what? R by root 2. That's it. So k is equals to r by root 2 is now the radius of gyration for a solid cylinder. Okay. You can similarly calculate it for anything as well. Anything. You can try reading out this one. It is an easy one. Let's move ahead. Yeah. So now there will be some questions like this as well. It's a good question, very good question, I would say. Take it as a homework. But one hint I will give you in this one, they're asking for like if you have to calculate the kinetic energy. So if you want to calculate the gain in kinetic energy, as I told you, it will be half I omega square. Where is this formula coming from? The formula comes from that kinetic energy is equals to half mv square. Converting it, it becomes I. Velocity becomes omega. So that's it. Half I omega square is the kinetic energy for a body which is rotating. That's it. Yep. Okay. Now, yeah. Similarly, we can make some extra formulas as well. Like if you want to calculate the formula for work done, or let's say power, you can also do it exactly in the same way. Now, if I want to make certain formulas, for example, how is this formula coming out? Torque is equals to I alpha. I already explained it, because force is equals to mass times acceleration. So force is converting into torque, mass into I, and A into alpha. This is how the formula comes out. Similarly, if I say power, so power is also equals to force times velocity. This is a formula for the power. This is not momentum. So the formula for the rotational version, power will be remain same, because it's a scalar quantity. Force will get converted into torque and velocity into omega. So similarly, you can make certain formulas. It's very easy. Yeah. Now, some questions I'm mentioning over here, try out doing them. They are very good problems actually, but you just need to understand the steps over here. Yep. Now, as I told you, the concept of conservation of momentum as well. So we know that force is equals to dp by dt. Yep. And if force is actually equals to zero, it's zero, then we can clearly say that momentum is actually equals to constant. This is a very simple thing, because the differentiation of a constant will give you a zero number. That's why. So same thing we can apply over here as well. Now, as we can say that the torque is equals to dl by dt, just like force is equals to rate of change of momentum, torque is equals to rate of change of angular momentum. Now, if the value of torque is equals to zero, then we can clearly say that what we can say, L will be equals to a constant. Yep. And as I told you, the formula for L, just like momentum is equals to what? mv. So mv is a constant. L will be equals to I omega. It is a constant, which means that as you can see, this is a very good example. When a body is rotating, so when you have a big uh, L over here, as you can like basically when the value of I is actually big, I means moment of inertia. As you have already increased the radius, then automatically moment of inertia will also increase. And if it is increased, then we can clearly say that what, like if it is rotating, if this is big, then automatically omega is small. When you have your hands are like this, in that particular case, you rotate slowly, as compared to if you want to rotate very fast, then you should make the moment of inertia small. You should make your radius small, and automatically you will start spinning fast. Very simple. Okay. Now, next is rolling motion. Now, rolling motion is a very, very important concept. One of the toughest concept in this whole chapter. Understand it. How do we actually go through it? If you are moving in a straight line, that's a translatory motion, rectilinear motion, whatever you want to call it. And we have already learned about rotational motion a lot in this chapter. What are we doing now? We are actually combining both of them. Our body is moving in a forward direction as well as it is rotating. This is a rolling motion. Simple. But how do we deal with it? So for dealing with it, we have to make certain concepts out of that. Yeah. So of course, I'm not going to make, what do we are not going to do all the derivations and all, but the important part over here is very, like, I will explain you how to deal with it. Imagine a body is rolling down on an inclined plane. So this is a particular plane from which a body is rolling down and coming down like this. Of course, so there, it can be any kind of body. It can be a ring, it can be a disc, it can be a cylinder, it can be a sphere, whatever. So I will not make separate formulas for all of them. I will make a single formula that will work in all the cases equally. Okay, this is what we are going to do. Okay, so the first thing is how much friction is experienced by the body. Yeah. So if the body is rolling right now, of course, you know that rolling friction is kind of a very small friction, but still, if it is there, how much is it? So body is moving here, friction will of course be in the opposite direction. How much is it? The formula is I alpha by R, or we can say IA by R square. Both of the formulas are actually the same. As you know that just like V is equals to R omega, then A is equals to what? R into alpha. Yeah. So we can simply say that from here, we can say that alpha is equals to A by R. So this is what we are actually putting over here to get this as the formula. So you can remember any one of them, and the second formula will automatically come out. Important point is this formula which we are making over here is actually coming from I only. I means moment of inertia. So now you can place the moment of inertia of any body. That is, you can place the moment of inertia of cylinder. You can place the moment of inertia of sphere, hollow cylinder, solid cylinder. You can place the formula of a disc. You can place the formula of a ring, whatever, and you will get the value of friction. Of course, separate body, basically a different body will experience a different friction. Second thing is how much acceleration the body is experiencing. Yep. So the general formula for the acceleration the body is experiencing, of course, if a body is coming down a surface, like if it is coming down like this, then what we can say that the acceleration will be g sine theta. It will be like this, that g sine theta by 1 plus I by mr square. Keep it in mind that g sine theta, g is of course acceleration due to gravity, sine theta is the angle with which the inclined plane is there. Yep. Next is I and mr square. I is the moment of inertia, so I is there. Most important part, again, if I take a certain example, for example a cylinder, so of course I will be equals to half mr square, and you will see this as a formula. So this is just my recommendation. Most of the times if you see a question based on this topic, it's a cylinder. I'm not confirming this, but most of the times. That's why you can remember this as well if you want. But again, totally up to you. If you want to ignore it, no problem. Remember this one. This is important because this is, of course, the general formula which will help you to calculate any of it. So it is important. If you want to, you can remember this one as well. This is for cylinder. How is it coming out to be? Because I is equals to half mr square, and we are just replacing it over here. That's it. Now, the last and the most important thing over here is the rolling without slipping or skating, whatever you want to call it. Sometimes what happens, you are on a inclined plane, you are coming down, you have applied your brakes, but still you are going down because maybe your bicycle is skidding, yeah, or your bike or car or whatever, it's skidding down. It happens. To, like, if you want that particular experience, or if you don't want that experience, you want the body to continue rolling, or if you want the body to skid, what are the conditions for that? So condition is very simple. That is, if you want to roll, if the body wants to roll without slipping, then the coefficient of friction should be more than or equal to 1 by 3 tan theta. Okay, very important, but very easy, but very important. If I will properly write it, that the condition for rolling without slipping, if you want to roll without slipping, then coefficient of friction should be more than 1 by 3 tan theta. Yep. Or of course, if you want to slip, it should be less. You know that. That's why you can see that it becomes very easy to skid on a ice plane. You can skid very easily over there because the coefficient of friction is less. Whereas on a rough road, the chances of skidding becomes less. Okay. So this was one of the most important things when we talk about the concept of rolling without slipping. Yeah. Then there is one more thing which I personally do not consider to be very important, but you can make it on your own. The formula is very easy. That is, if you want to make the formula for kinetic energy. So because it's a rolling motion, not only a rotational motion, there are two motions involved in this particular scenario. That is, the body is moving in a forward direction. That is the translational motion as well. Body is rotating at the same time. That is the rotational motion. What do you need to do? Add both of them. You will get the total kinetic energy of the body. That is kinetic energy of the center of mass, kinetic energy of center of mass, including the translational and the rotational. Translational you are doing from your childhood, that is half mv square, and for rotational I just taught you, it is 1 by 2 I omega square. That's it. This is how you can calculate it. We are done with this particular chapter today. Yep, it's a tough chapter, I know. So take your time, do easy problems first, then go on to tough questions. This is how you will be able to manage this chapter. Yep. So try making a routine for this one, that today I will try to remember the moment of inertia of certain bodies. I will solve some problems. So the whole thing will be done like that. Your main priority should be doing questions as much as possible. Once that's done, the formulas will automatically be done. Okay. Bye bye. Thank you so much. That's it for today. Bye.